So hello guys, I'm Eric Chan Habal, and this here is my individual project for assignment 2, which is simulating the circuits for multiplexers and demultiplexers. So uh, as we can see here, this is our first multiplexer circuit. Um, we we don't we didn't use the multiplexer first, so we're just gonna demonstrate the switch. So for the switch at its zero state, we can see that the truth table for this first, uh, before we analyze the circuit, is this. So we can see here that the X only returns A1 when A A is 1 and B is 0, and A is 1 and B is 1. So if we plot that at a K-map, we can easily see that uh, they are next to each other, and that the common term between them is A, and we can simplify that as A. So when we go back here, so we plotted S at 0 and A at 1. So S naught and A, which stands for these values of X at 1, at A, B naught, and A, B. So the next values which X returns to 1 is at S is 1 and B are 1s also, but A is any state. So that we put S at 1 and B at 1 there. So this is our multiplexer circuit equivalent, but when when we get an actual multiplexer, this here is what we have. Yes, so to demonstrate, let's go here. So when we 0 0, it's 0, at A is 1, and B is 0, it returns 1, and B is 1. Yes, and at switch 1, B at 1 and A at 0 is 1, and B at 1 and A at 1 is 1. So we have that, and when we go to the multiplexer, we have that at A, basta A is 1, we have a result 1 at switch 0, and at switch 1, we have a result 1 since B is 1. So let's move on to the second multiplexer circuit. We have here the A multiplexer circuit, which combines the AND functions and the XNOR functions. So we can see here that when the switch is at 0, we only use the AND function. So you can see here that it only returns the value of the AND part. And if we switch that at 1, it returns the value of the XNOR part. So when we use a actual multiplexer, this is what the circuit would look like, which is simpler since it only uses and XNOR and not the and additional and gates. So yeah, we can see here that the end returns and XNOR. Yes. So let's move on to the third multiplexer. Oh, let's compare first the circuits. So yes, this is the circuit, the truth table for this first multiplexer equivalent, and this is the, yes, when you switch the S there, it is still at that one. Yes. So here in number 2, we analyze the circuit there. Ignore the small x and y's, so we only look at the big X. So, and when we look at here, it has the same. Actually, Well, you get the gist of it. Oh, it's actually switched. So I'm sorry. So at S, yes, yes. So at multiplexer, the third multiplexer we have, so it fulfills. It's like the second multiplexer, but we have the different gates. So we choose from a variety of gates, and it is a 3-bit multiplexer. So you can see that it has 1, 2, 3, 4, 5, 6, 7, 8 inputs, since 2 raised to 3, the 3-bit is equal to 8. So at 0, 0, 0, it returns the value for the first 0, 0, 1, the second 0, 0, 1, 0, the third, and so on and so forth. Yeah, there we have that. You can see the 0 here is equivalent for the 6, and for the here is the 6. My bad, this is the 5. So here is the 5. Here is the 6 switch, which is the adder, and here is the subtractor result. So we have that. And for our demultiplexer, so we have here. Uh, so we have two switches. It is a 2-bit switch for the demultiplexer. So we have the output 1, output 2, output 3, and well, output 0 technically here, and output 1, output 2, and output 3. So that is our demultiplexer, which chooses the output. So we go here to the our demultiplexer. So here is a simple demultiplexer for an adder, a 2-bit adder. So when we add 1 here with 0, it returns 1. Yes, and the demultiplexer chooses what result would be how the result should be shown. Uh, so when we add 1 and 1 here, the result is 2. Uh, and for the first method of the result, we have the actual bit, and here the second is the LED. The third is another LED, but horizontal, and the fourth is a uh, yeah, 7, do you call that? 7-segment LED something. So yes, it returns 1, returns 2, returns 3, and for just it doesn't compute, since it only displays 2-bit results. And we can see here that this decoder, it goes here to this decoder, and this decoder is here. So I coded that so that the, these lines here respond to a certain S on and off, so bit. So I just coded that A0 would have the result of these outputs 1, 1, 1, 1 for B, C, D, E, F, G, and they are connected accordingly. And for 1, wait, so this for 1, yes, it only lights up 2. For 2, it lights up 1, 2, 3, 4, 5, and for 3, it lights up 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. I mean, so that's how we coded that demultiplexer. So uh, that